Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 67. 67. Alright, so last lesson I said we might do some self-balancing binary trees, so ones that are a little more efficient in general because they try to balance the number of sides to keep it from becoming a linked list. I've decided to hold off on that. Instead, we're going to do a little visualizer here first, see if I can do it. So, well, see if we can do it in time, I guess, because I already did it, so I know I can do it. So, I'm going to do a little visualizer program, though. So, let's go ahead and begin. So, we're just going to give us a little menu, and as we go through the menu, we're going to add the various functionalities we want to visualize. So, let's begin here. Let's create a public class BST node. So this will be just a class we did the other day. So public int value, public BST node left, and just grab that and make it right. So there's just our node, and here we'll cast it to its own file. So we'll also need a public class BST. So this is our search tree class. So we'll have public BST node. So there's the root. Let's see, we'll have a public void. Let's see, we had insert a value, throw new not implemented exception. We had public void search int value. We want that, but I want it on a separate line. And public void delete int value. Like that. So there's just the three classes, or three methods we'll be filling out today. And they'll be very similar to what we filled out the other day. Let's do one more. We'll do public void print in order. BST node. And here we'll just do our print so we can get an in order print. All right. So there's just our structure of this class. So we'll move that, cast it over here. That one. That was the one I did not want. Let me open our one last time as well. Let me just grab out my text file here. Trees.txt here. So we're going to do this one sideways. So I'm just going to grab that. Let's see, add a new item, new text file, trees.txt. Move to the right group. Make it really small over here on the side. Okay, there we go. So that's pretty much got the structure we want to do. So let's go ahead and create the main class. So we're going to do one more class here. We're going to have a public static class tree printer. So this will be our class that actually prints the tree, and it's going to be recursive, and it's going to have a single method, public static void print. So this one takes in a node, an optional node. We'll say root int indent equals 0. So what I'm going to do here is I'm just going to indent it, so we're going to transform this tree to be on its side. So let's see if we can do this. So if root is null, return So now we want to print root dot right indent plus, we'll do probably, let's do 4, but we might switch it to 2. I tried both and we'll see which one looks better. So here now we'll do this. So I'm trying to think how I don't want to do this. So I'm wanting to add some spaces, so 4 spaces. We'll just do it like I did here. I don't know if we've done this before, but we'll do it here anyway. So what that gives you is, we'll do root dot value. So I don't know if I actually used new string before like this, but it lets you do a new string with a specific count. So you have the character you want, so space, and I'm saying number of ones to give is this indent. So 0 or +4 or +4, and that way we build up the count. I actually don't know if we've actually used that before, but that's how you can use it. And then we just append the root on at the end. Could be more efficient and do a string builder. I don't think we're going to have the efficiency there, though. I think this is going to be just fine. So we'll do root dot left indent +4, and we're done. So one thing that happens here, if you have ReSharper's analysis thing, an analysis provides code insight, like tells you things that you can do to change how it works. This will note that this is a tail call recursion. That means it's recursion happening at the end and it's not returning a value or anything. And for that, you could actually convert this to a while loop, or a loop. I would think while loop, but you could convert this to a loop and do it like that instead if you wanted to. I'm going to leave it as the recursive one because I think it makes more logical sense, but we could do this a different way. We could do it like, let's see if I can convert it. So I think we'll just want to, here, let's wrap the whole thing. I was going to just add a while loop. I think we can just do right click, snippets, surround with while true. If it's that, this one's still correct. This one's still correct, but here at the end, we would do root equals root dot left indent equals indent +4. And that should be plus equals 4. And I think that gets us the same thing. So I think that will be the same result, but we'll keep it as a recursive one because I think this one's cleaner. But if you have an analyzer, you might get a notice there. Mine's over in Rider, it's an info, but just a heads up. So there's this little helper class. So we'll move this one to its own file. And now let's write the main program. So to begin, let's create a binary search tree, BST. All right, so now we'll do the main loop. So we'll need, let's see. Let's do this. We'll just do it like I did before. So we'll have a little menu here to know what options we have. We'll make the second option search. Make the third option delete. Fourth option print tree. Make the fifth option, and I'm breaking with my thing here. We'll do print in order. And then finally we'll have an exit. This is not the order that I did. Did in practice. So what ended up happening in practice is I got the first 3 and then exited, and then I was like, I think I'd like to be able to see the tree, and then added them later. So did it in the worst order. So for input, console.readline or empty string. Now we'll switch on input, case 1, break, case 2, case 3, case 4, case 5, and case 6. And I guess yeah, we could have an error case. Instead of error, we'll just reloop. So let's do here. So case 1 for insert. Insert's pretty easy. We'll do console.write value bst.insert int.parse, and I'm not doing the if we give something wrong here, we'll have a problem. But so we're just gonna do the parse line there and just assume that it's good. Now we'll use our printer. Print. There we go. I think that's all I want to do here. So case 2, it's going to be exactly the same thing. So let's just grab this, and we will say, instead of insert, search. So make that match, and we won't even do the print there. So we'll just search, and we'll have we're not doing this good and separated, so we're having the insert and search and delete and everything do their own printing, because the order I'm doing this in. Oops. Same thing here. Value. Delete. After delete, we should probably print again. Show the tree that you deleted from. For this one, it's easy. It's quite literally just print it. For this one, it is print in order root. And for the last case, it's just return. Okay, so I think that'll get us the console class. So just a little class here. I can remove that. That is not what I wanted to do. Okay, there we go. So there's our class. So now we've got a program to actually run, but all the logic's still not implemented. So let's implement the logic. We're going to start with the last one. So in order. So if we remember, in order is pretty easy. So if node is null, return, else in, we'll do print in order, node.left. We'll do it like this. So we'll do node.value plus that. And then we'll do print in order node.left. That should get it, not left, right. And that should get us our in order printing. So let's do insert. So insert. So here we'll print it out. So CW. So let's get a new line. Insert value. There we go. And now we're going to do this. Root equals insert at root value. So what am I doing there? So we're going to have a private method here that actually does the insertion. So private BST node insert BST node int value. So if node is null, here we'll put this inside here. So we'll do CW I forgot how many spaces I needed to line this up. Looks like it's 2. 1, 2. Yeah, 2 spaces. Okay. So what I did is line this up, but then I don't know what I lined it up to. So something like this, and then return new BST node value equals value. So that's the if it's null, we just return a new one with the value. If value greater than node or less than node.value. So in this case, we put it on the left. So something like this, 2 spaces, value, node.value. And then we'll do node.left equals insert node.left value. That should get us the left side. Else if value is greater than node.value. Now we'll do the insert to the right side. So let's see. So everything's the same until we get to one of the lefts. So then we'll say right. Right. And right. So there we go. So now we've got us a right side. The other case is if it's equal. And we're not allowing duplicates. So we'll say value already exists. I think that'll be better than the message I put before. I just said duplicate last in my example. All right, so there we go. So I think that'll give us an insert. And it could be static. I don't think I care. I guess internally it doesn't matter, so we'll just do that. Okay, so let's do search. So search is very similar. If we remember, we'll do the same thing here. We'll do search value return search root value. So I'm doing a return there, so let's make this a bool. Let's make sure we didn't break anything over here. I don't actually catch it, so I don't care. Private static bool search BST node int value. We'll do it like this. All right, so same cases here. So if node is null, then we'll do CW reached null not found. We'll say, let's do it like this. Value not found. return false. At node.value. So this is where you're starting the search from. If value equals node.value, CW found, return true. So else, now we'll do the other side. So if value is less than node.value, return search node.left value, else return search node.right value. So once again, you'll get a even better. Let me do this. We can do this as well. Yeah. There we go. So this, you'll likely also get a warning if you have resharper or anything. So again, the warning saying the same thing. Tail recursive call can be replaced with a loop. Here we can actually do even better than this, but let's see. So we could do, instead of this, we could do this would also be valid. I don't like this one though as much, so I'm going to keep it the way I've done it. Now you might like that because it's one statement. I don't personally like having the value inside here. I actually don't mind this one. I don't like this one though. You could do that. You can also do the tail call recursion. So the reason you might consider doing that is it makes it iterative instead of recursive. So this is recursive, so it'll have to keep going down the list. And if you get too many, you'll get that Stack Overflow error we seen several videos ago. If you do it iteratively, you won't run into that. So you'll get a little better performance, but it's less understandable. And in this case, it's not that much less understandable, actually. What it does is it puts a while here and then sets the node here to this value rather than doing the search. But I'm going to keep the search and keep it recursive because to me that makes more sense. But if you were to try to do something like this and ran into Stack Overflow problems, that's likely the problem, is that you're here at the end, you're just recursing when you don't need to. But that should get us a search. So let's make this static and let's do delete. Oh, wait a minute, let's not do that one static. Yeah, let's not do that one because that one actually changes the semantics on the other side. So let's do delete. So delete was the harder one, so we'll begin like this. So don't write line just like the others. Delete value. And then root equals delete root value. Okay, so now let's implement delete. So we'll do public static est node delete int value. All right. So first case, if it's null, value, we didn't find the value. So if node is null, CW value not found, return null. So otherwise, now we need to go through the cases. So first case, the value is less than the node. So if value is node.value less than node.value, now we'll do this value is less than node dot value, go left. Node dot left equals delete that. So the next case, else if value is greater than the node dot value. Now we'll do console.writeLine. Value is greater than node dot value. Go right. Node dot right equals delete node dot right value. So there will be us the right case. That's we're going down either side of the subtree checking for which value we're going to delete. So else we found the value. So we found the value we're trying to delete. So else we'll designate that found value deleting. So no children. So if node dot left equals is null and node dot right is null, CW leaf node removed. So that's the easy case. Return null. So that's the easy one. So by the way, you just seen when I was writing that I was going equal and then swapped to is. The reason for that is technically not required in this case. Our node here doesn't do anything special. So if we customize the equals, like we could override the equals and do our own equal method and make it do something completely different. It'd be bad design, but you could do that. The is check doesn't let you do that. So you can override equals. You can't override is, however. So that means it's always going to check, is it null? And it gives me the check I'm expecting. That wasn't always available, however. So whenever I started, it was still equals, and that was just what you had to do. And if someone overrode it, they caused problems. And you probably don't need to override it, but just if you did, that's the reason I do the is instead of the equals, but you still occasionally, I'll just go to equal, and I was like, well, no, I want to use is. But that's just a thing there, not really a reason not to choose one or the other unless you're in a code base that overrides the equals a lot, and at that point there's other problems. But I've just got in a habit of trying to do is instead, but that's what you'll see me if I'm typing. I'll try to do equals, and that's just what's happening. So let's do the next case. One child. So if node dot left is null, one child, promote right. Return node dot right. If node dot right, see, I almost typed equals right there. Even after just talking about it. Promote left. Return node dot left. All right, so there's the middle case. So the last case is there's two children. And this is the trickier case, but not that much trickier. So let's do this. So we'll do two children. So we'll do CW, two children, find successor. Var successor equals find min node dot right. So let's define this method. I did it as a separate method. I could technically do it in here as an internal method. I'm going to keep it as I did it, but we could do it separately if we needed to. While node.left is not null, node equals node.left, return node at the end. There we go. So there we found our successor. All right. Successor is successor.value. Node.value equals successor.value. Node.write equals delete. Node.write successor.value. Okay. So I think that gets us everything if I haven't made mistakes here. It looks like we've made a mistake. All code paths return a value. What did we miss? Oh. We didn't actually return the node at the very end. That was easy. So now we set all the values and we return whatever the node was. So that should get us our method here. So that sets everything up. So let me just mention the reason I didn't swap the in order here is because it causes us change. If I make that static, now if I go over here to program, I had to do something different. I had to add this BST print in order instead of BST insert. So the difference there is I'm calling the class method print in order versus the instance method, this one, the instance method. Not really a major reason to do one or the other. Technically, this one's probably fine. It's when you get into testing that you might run into you like one or the other better. For this specific case, it doesn't really matter. It's just it changed how I was calling it. So just a note there, but I'll go ahead and leave it because it's going to be the same thing for our purposes. But that's the difference there of having that one method be static or not. All right, so let's run this and let's create this structure here. We'll see if we have any bugs in here, which we very likely will. All right, so let's begin. So again, we didn't do any validation. If we took the time to make this an actual program, we could do that, but we won't do that for now. So let's do insert value 10. All right, so let's try to make the tree look like this tree here. So now we will insert 5, insert a 15, insert a 3, insert a 7, insert a 6, insert an 11, insert a 20. All right. So I should try to draw the lines, but I didn't do that. You can sort of visualize the tree here, 10, 15, 20, 11. So that's this side. Over here we have 5, 7, 6, 3. So it sort of looks right. So we can print in order, and we see we get the sorted order, which is nice. If we print a tree, we get the same visualization we just seen a second ago. So let's search for value. Let's search for the 11. At node 10. So what happened? So it started at 10. Then it figured out it was greater than 10, so it went to 15. Then it figured out it was less than 15, and then it went to 11, and then it was found. So search worked for that case. What if we search for something that's not there? Like, let's search for 8. So at node 10, less than, node 5, greater than, and node 7, greater than, but we found null, so 8 was not found. That seemed to work. So let's delete a node. Let's see. Let's delete Let's delete. Let's delete 5, I guess. I wanted to delete a leaf, but I think we'll delete the leaf in a second. All right, so let's delete 5. So 5 is less than 10, so we go left. Now we found 5, deleting. He has 2 children. So we need to find a successor. We go down this side. Successor is 6. So then 6 is less than 7. So go left. So then we got him down here. We delete 6. That removed a leaf node, and we're done. So yeah, I think that worked. So let's delete 3 at this point. So there we go left, found 3, deleting. It is a leaf node, so we just removed it. That worked out. Let's do one with 1 child, I guess. Let's delete 6. So there, we got to promote right, and we just promoted right to 7 and deleted it. So that one worked out. So let's do one more. We'll delete 10. And there we go. So found 10, immediately found. It has 2 children, find a successor. Successor is 11. So we went down the list. Down this one. So 11 is less than 15. So we went down 1. Found 11 is less than 15. So then we found this node. Then we set this node to 11. We delete this node. And we're left with this tree. So let's insert a couple nodes here. Let's insert 21, insert 21 again. Already exists. Insert 22, insert 23, insert 24, insert 25, insert 26. And look at that. So we're still making a tree, but all the inserts are being worst case in this case. So we're getting a line. So that's, so if we search now, let's say we search for, say 30. So now we had to search through 11, 15, 20, 21, 22, 23, 26, and we didn't find 30. That's looking very much like a linked list. So this is highlighting the problem with binary search trees is if you insert sorted data, you're going to get a linked list and you lose all the benefits from the search tree you had from searching or other searches up here or a long time ago, apparently. We just had to go through 3 nodes to find 11. So that's the importance of balancing the search tree. Like if we were looking for 7 here, we just have to do 2 searches. Having a bigger list, it's harder to tell. So originally planned for this lesson to be a AVL tree, which is an attempt to balance this better. So instead of getting, instead of getting that structure, the linked list structure, you sort of instead try to keep it a little more balanced. And we may plan for that next time, actually. So we may try to add a new method here, maybe, or add some new inserts, or may have to do a slightly different visualizer. I'm not sure, but I'll think of what to do there, and we'll introduce AVL trees probably next time. So let's go ahead and let's just print in order, just to print one more time. Looking good, and then we'll exit. All right. So that's pretty much going to do it for today. That's what I wanted to do. I was, like I said, I was going to do the AVL tree today, but I was thinking through, and I was like, let's see if we can't visualize it. And I was trying to visualize it like this, and I could get something like this. It was a lot easier just to do the growing from left to right. So that's what we ended up going with. But if you wanted to, you could definitely program something that does that. But yeah, I think we're going to call it with that. So this is a visualizer for a binary search tree. So a good little aside, and hopefully seeing it a second time and doing it slightly differently, drawing it differently at least. Maybe we didn't do them. I think I even did the same methods, probably actually didn't. I'm not 100% sure, but I think I copied it and started from what we did last time. But if not, it was pretty close. Yeah, well, I think we'll call it there. One thing, or apologies for the black bars at the top and bottom. I usually turn off the taskbar, like hide the taskbar while we're doing this. For whatever reason, Windows' latest update broke that, so you can no longer hide the taskbar for some reason. So I've just left it there, and I've just cropped it out. But in doing so, you get some black bars. It looks like I've mostly got them up the top of the screen. Not really important, but just wanted to mention that in case anyone noticed and is not used to seeing that. Yeah, I don't know which way to go, but yeah, I think I like it better at the top. But yeah, so that's that. That's pretty much all we're going to cover today, though. So this has been Programming with Shadow, episode 67. Thanks for watching, and have a wonderful rest of your day.